The real and imaginary parts of z don't really act together. They are sort of separate beasts. So for example, say I have two complex numbers. I'll call z1 4 plus 5i, and z2 3 plus 9i. I can compute the sum, z1 plus z2. This is done by taking the real parts and adding them together, and then taking the imaginary parts and adding them together. The imaginary parts are still multiplied by this thing called I. And this works out to be 7 plus 14i. So in this sense, I haven't done anything between the real parts and the imaginary parts. They've acted separately. I've added them separately. We can also compute the difference between z1 and z2. That's just the difference in the real parts and the difference in the imaginary parts. And this works out to be 1 minus 4i. Now this thing called I is defined as the square root of minus 1. So I squared actually equals minus 1. This gives a funny feature about products. So for example, z1 squared, what does that equal? That's 4 plus 5i times 4 plus 5i. And if I multiply that out, that's 16 plus 2 times 4 times 5i plus 5i squared. Well, that's 16 plus 40i minus 25. That comes from the fact that I squared is minus 1. So in fact, this equals minus 9 plus 40i. And if you're used to the idea that the square of a number is positive, we have to let go of that here, because here now the square of z came out to be not necessarily a positive number in any sense. It's still a complex number. There is, however, something which is positive for complex numbers. And that's called the absolute value. And this is defined as the square root of the real part squared plus the imaginary part squared. So in a sense, that's a lot like the magnitude of a vector, or the magnitude of a radius or something. So in my example here, if I wanted to calculate the magnitude of z2, this would equal the square root of 3 squared plus 9 squared, and that's defined as 3 squared to 10. And that always is positive. But that is a different beast than the kind of absolute values we're used to.